Hello again, AP Stats. This is Mrs. Harding. Today we're going to do activity 2.2b, as always located in your class 1 note. If you remember back to what we did in 2.2a, we had talked about density curves, and then we began to look at the normal distribution, unimodal and symmetric, and you were introduced to the empirical rule, which estimated what percent of the data fell within 1, 2, and 3 standard deviations. Today we're going to look a little more closely at a normal distribution, and we're going to find other values. So you see the learning objectives at the top. Find the proportion of values in a specified interval in a normal distribution using table A, I'll explain that, and technology, which is your calculator, I will explain that also. And then find the value that corresponds to a given percentile. Remember, percentile is the percent of data that falls below a given number. So let's come back to the example here at the top of activity 2.2b. It discusses a comparison between the SAT and the ACT. Now, all of you are familiar with these tests, and you realize that they are scored on two different scales. A perfect score in the SAT and a perfect score in the ACT are very different numbers. And it gives you some information about the mean and standard deviation in a given year. Suppose in a particular year, the mean and standard deviation for the SAT was 896 and 174 respectively, and the mean and standard deviation for the ACT was 20.6 and 5.2 respectively. And it does indicate there that all of these scores can be modeled by a normal density curve. So if we have two people, James, who scored a 1080 on his SAT, and Kathy, who scored a 28 on her ACT, how would we compare who actually did better? Well, we want to do it by comparing where they fall within their respective distributions. If all you did was just look at how far above the mean each of them falls, I apologize, I'm going to have to flip screens there. It doesn't really tell you much. They certainly both scored above the mean, but because they're measured on different scales, you can't really tell. But if we compare how well they did using the mean and the standard deviation, and we standardize their scores, now they are on the same scale with a mean of 0, standard deviation of 1, and then you can actually compare who did better. If you standardize both of their scores, you can see that James was 1.06 standard deviations above the mean, whereas Kathy was 1.42 standard deviations above the mean. So Kathy actually did better with her ACT score because she scored better relative to the rest of the distribution. Now this is just exactly the standardized formula that you had talked about in the previous activity. We're going to call these a z-score or standardized score. For any value, you take the value minus the mean divided by the standard deviation. And you can see some new notation in there if you remember mu and sigma, the mean and standard deviation on a normal distribution. So we can do this again for question 5. It says Peter scored 740 on the SAT and Kelly scored a 19 on the ACT. Calculate their z-scores. All right, we have their z-scores there. This time they're negative. What does that mean? That just means that they fell below the mean. So Peter had a z-score of negative 0.89, so he is 0.89 standard deviations below the mean. Kelly is 0.31 standard deviations below the mean. That's what a negative z-score means. So who scored better? Kelly scored better. What would a z-score of 2 mean? 2 standard deviations above the mean. A negative 3 would be 3 standard deviations below the mean. Be sure that you're talking about these values in terms of standard deviation as opposed to saying points or percentages or some other language. It's specifically the number of standard deviations above or below the mean. Now, if you look in part E, it's asking you to work backwards. You have a z-score there, and it's asking you to compute the actual score. So I'd like you to pause the video and answer the question in part E. Okay, you can check your answers there. We're just working backwards with the formula, multiplying by standard deviation and then adding the mean to get the actual score. All right, let's switch over and take a look at an actual standard normal distribution here on the next page. So these are all standardized scores, which makes the mean 0, the standard deviation 1. You can see the highlighted portion there is the notation that shows that. And what we're going to do is we're going to look at the math placement data from section 2.1, and we're going to convert these to a standardized score. So if you remember, here was the distribution of scores. At the time, we had looked at specifically the value of 7, and we calculated the percent of data that would be less than or equal to 7. We calculated the percentile. We said it's roughly 25%. And if you look on there, we had drawn a density curve, the shaded area, roughly 25%. Well, we're going to model this with a standardized normal density curve where we're going to use a mean of 10.2 and a standard deviation of 3.8 to find the z-score for 7. You can see the z-score there is negative 0.83. If you go back to the standard normal distribution, negative 0.83 is about right there. And I'll have this drawn on the next page. If that was exactly at -1, we could come up with a rough estimate of the percentage, but it's a little bit off. So we're going to have to take a look at other methods for finding the distribution. Finding the percent within the distribution. So flipping to the next page, it has negative 0.83. The area to the left is shaded. Does this appear to be about 26%? It does. But how could we find specifically what that area is, because it's not falling at an even standard deviation? This is where we're going to start using a table of values to find the area to the left of a given z-score. So we'll be able to look up negative 0.83 exactly, and it will tell us the area to the left. And we're going to use the next example, and I'll show you how to use the table to find this percent. In the next example, we're going to go back to Kathy's ACT score. It says, recall that Kathy's z-score for the ACT was 1.42. We estimated her percentile rank at around 90%. This is the area to the left of 1.42 under a standard normal curve. All right, so let's actually scroll to, let's find 1.42 here on the standard normal probability table. So if you recall from Algebra 2 when you were first introduced to this, how to read this table. The ones and tens place you can find in the column, and then you follow it over to the hundreds place. So 1.42, you're going to go to 1.42, 1.4 is here, and follow it over to this column. That number right there tells you the area to the left of a value of 1.42 on the standard normal curve, 0.9222. And that is referenced here in the description. You can find the area more precisely. You can see the value in the body of the table is 0.9222. This is the area to the left. So Kathy's percentile rank is actually a little bit better than what you might have estimated before. She is in about the 92nd percentile. So it should follow what percent is above the score, 1 minus 0.9222. 100% of the data is underneath, subtract out the percentile. So about 7.78% of the people in that distribution scored better than Kathy did. And you can see that we could do the same for James' score. We could look up Z as 1.05 and get that percentile there as well. This table that you're looking at, I'm going to sidestep from the activity for just a second. A standard normal probability table is something that you'll be given for the AP exam. You can also get these values from your calculator, which I'll show you that in a little bit. But also at any point when you're working at home and you need a normal distribution table, just Google it. That's all you have to do is type it in. You'll have 100 images to choose from. It's a pretty common thing to find online. But specifically, I want to show you that there is a formula sheet, and this is the first time that we're talking about this formula sheet. I'm going to send my classes this formula sheet through OneNote. I'm not sure how Mr. Bowman's students will get their formula sheet. You may want to ask him for it, but this is the formula sheet that you'll get for the AP exam. We are introducing it now because it's starting to be a little bit more relevant. You can see in here a couple of formulas that have been discussed. The mean formula and the standard deviation formula. We'll eventually get through all of these. It's a multi-page formula sheet, and at the end of the sheet is the standard normal probabilities. So you also have this right in your class 1 note anytime that you need to use it, and it will be given to you for the AP exam. So that has been distributed to you for any time that you need to reference that. But let's go back to the questions. Oops, forgive my scrolling for a minute. Let's get back to where we left off. We left off here. In part D, it says using the table above, find the percentage of students who scored below 7 on the math placement exam. Recall that z-score was negative 0.83. So one thing that you'll have to do when you're using a normal distribution table is round to the hundredth place. We can use more places if we're using our calculator. But there's a couple of things to pay attention to. First of all, this is asking what percent scored above. Oh, I'm sorry, I'm completely getting ahead of myself here. When you're looking at this normal distribution table, a normal distribution is symmetric. So you'll notice that in the table that I've given you in the middle of the activity is only positive values. If you had to find a z-score for 7, which was down here at negative 0.83, right? I wanted to know this percent of the data. You can still use just positives on the normal distribution table by thinking about symmetry. The symmetry in here would be saying that the area above positive 0.83 is equal to the area below negative 0.83. So you can see from the work that's done there, Mr. Bowman looked up positive 0.83 and then just did 1 minus that value to find the amount that's below. So you can use symmetry here to come up with those values. So in that way, you actually don't even need the negative z-score values in the table. You can just use the positives and the idea of symmetry in the normal distribution to come up with the percentages that you need. Okay, so at this time, I'd like you to pause the video and then try and answer the questions on the next page to find the actual percentages that fall between or below or above a given z-score. Okay, you can go ahead and check your answers. Question number 1, simply looking up 1.39, seeing the area to the left. Question number 2, on the other hand, asks for a z greater than negative 2.15. So you need to keep in mind that the areas that you see in the table are to the left. They are always less than the given z-score. So when you look up negative 2.15, you need to subtract from 1 to get 0.9842. Here in question 3, the area that is between two z-scores, you just need to look up both z-scores and subtract the percentages that you see to get 0.9019. Now, to move in the other direction, to be given a percentile and then need to find the z-score that cuts off that percentile. In question 4, it asks for the cutoff z-score for the 20th percentile. What this is going to require you to do is to look up 0.2 in the middle of the table and then follow it out to find the z-score that corresponds. So you're just going to get as close to 0.20 in the table as possible to get a z-score of negative 0.84. In number 4, it says 45% of all observations are greater than z. So if we're using the table, we're looking here for 45%, but what you're going to have to look up in the table is the cutoff value for 55%. And when you find as close as you can to the middle, in the middle of the table to 0.55, you come up with a z-score of 0.13. Okay, so let's try and put all of this together for a problem in context. If you read at the top, it's talking about the cholesterol levels of 14-year-old boys. It says the distribution is approximately normal with a mean of 170 milligrams and a standard deviation of 30 milligrams. Suppose that for 14-year-old boys, a cholesterol level greater than 240 would require medical attention. So based on this statistic, what do we know about the percent of 14-year-old boys who have that particular cholesterol level and need medical attention? So the first step in solving this is to figure out where this falls on the standard normal curve, on the normal curve. Apology. Let's take a look. Sorry about that. I get a little thrown off when my screen won't scroll, but here we go. So on a normal distribution, you have a mean of 170 mark there. 240 is certainly above it. And so we're trying to figure out what percent of 14-year-old boys fall into that shaded region on the normal distribution. So what does this shaded area represent? This is the proportion of 14-year-old boys with cholesterol levels over 240. So what we're going to do to answer this question is we're going to standardize the score. So the standardized score for that cholesterol level is 2.33. So that would be anyone that is 2.33 standard deviations above the mean or more. Okay? So we need to figure out what percent of the data that is. The third step is to find the area sketched in Part B. To do this, we can look up the area in a table as described previously. Well, remember in the table gives you the area to the left. So you're going to need to do 1 minus the area that you see in the table. And you can see from the screen that you have a value actually from your calculator. So I'm going to sidestep for just a minute and I'm going to show you on the calculator where you can find this information. So pull out your calculator. Do you see the variables key here? And above it, it says distributions. So I'm going to hit second, variables. And what I'm looking for is a normal CDF, cumulative distribution function. So if I hit number 2, this is going to ask for an upper and a lower bound of the standard normal curve. Remember that the ends of the curve go on infinitely, so the lower end is just some very, 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 very small number. So I'm going to leave that alone. The upper end is that cutoff value of 2.33. This is going to give me the area to the left of a z-score of 2.33. On a standard normal curve, the mean is 0, standard deviation is 1, and then you will see that on the screen. So when I hit enter, this is the area to the left of a z-score of 2.33. I actually want to know the area that's to the right, what's greater. So I'm going to do 1 minus that answer. And this is the percent that represents that shaded area on the activity we were just looking at. So you can see it's roughly about 1%. So then to answer this question in Part D, we're going to make sure that we answer in context. So about 1% of 14-year-old boys have cholesterol levels of 240 or above. All right, let's take a look at a couple more complicated calculations that you might be asked to do. In Part E, it says people with cholesterol levels between 200 and 240 are at considerable risk for heart disease. What percent of 14-year-old boys have blood cholesterol between 200 and 240? This just requires us to find additional z-scores on the standard normal table and then finding the area in between. So the standardized score for 200 is 1. The standardized score for 240 again was 2.33. If we look at the percent of boys that are below each of those, 0.99 and 0.84, we're looking for the area in between. So about 14.88% of 14-year-old boys have cholesterol levels between 200 and 240. We can also relate these back to the quartiles and actual percentages. So in Part F, we're looking for the first and the third quartiles. Now remember that this distribution is symmetric. So here, 0.25, I want to find the cutoff z-score for the lowest 25%. So I'm going to look in the center of the table to find as close to 0.25 as possible, and you'll come up with a z-score of negative 0.67. Because this is symmetric, that means the third quartile, which marks off the top 25%, would have a z-score of positive 0.67. So then I need to work backwards from negative 0.67 and positive 0.67 to find the actual cholesterol values that correspond to those quartiles. Now you want to be careful with this. Sometimes people will just find one of them. They'll just find the 150 that you see on the screen, and they'll say, oh, it's plus and minus 150. That is not accurate. The plus and minus are the z-scores. That's what's symmetric. You still need to go through and find the individual values in context. So the first quartile would be marked off by a cholesterol level of 150. The third quartile would be marked off by a cholesterol level of 190. Moving on to the last page. So sorry, I'm not sure why my screen does not scroll very well. It says, how high would the cholesterol level need to be in order for a 14-year-old boy to be at the 90th percentile? So all we're looking for is 0.90, as close as we can get in the center of the table. Follow it out to the margins to get a z-score of 1.28, and then convert that back to an actual value in the context of the problem. All right, I'd like you to stop the video here, and I would like you to complete the check your understanding. All right, you're just going through a new scenario here. The likely expenditure of customers at the supermarket, it's normally distributed with a mean of 50, standard deviation of 15. For part A, find the proportion of shoppers selected at random that spend more than 80 per week. Convert 80 to a standardized score. Look that score up in the z-score table, and then subtract from 1 because you're looking at the proportion that spend more. Find the proportion of shoppers that spend less than 50 per week. You can just do 1 minus. Oh, I'm so sorry. I'm getting distracted by my screen, not scrolling. Hang on. Here we go. Part B, find the proportion of shoppers that spend less than $50 a week. No calculation needed. 50 is the mean, so it's 50%. Part C, find the percentage of shoppers who are expected to spend between 30 and 80. You're finding z-scores for both of those and finding the area that's in between. And on the last page, determine the expected number of shoppers in this sample who spend less than 70. Convert 70 to a z-score. Find the area below. And that is the percentage of total shoppers. The question here is saying the expected number. So out of 500 shoppers, about 90% of them would be 454 shoppers would be spending less than 70 per week. Same thing here in part E, determine the expected number of shoppers. First, you want to find the percentage of shoppers that would spend between $37.50 and $57.50, and then use that to determine out of 500 shoppers how many that actually would be. It would be roughly 245. And then the last question, suppose that on a particular test you know that the scores are normally distributed with a mean of 83%, standard deviation of 7.8. If you had a standardized score of negative 1.2, what score would you actually have? And you're just working the standardized score formula backwards. You can check your answer there, 73.6. My apologies, I was getting distracted quite a bit in here about my screen not scrolling. If you have any questions, please remember to ask Mr. Bowman or I during class.